Okay, we are live. So, last of the things we need to learn about curve sketching is when you are concave or convex, when you have a concave up or a concave down, and how you use the second derivative to figure that out. So we learned that critical points of the first derivative, or the critical values that the first derivative tells us, which are critical points, don't necessarily have to be local maximums or local minimums. They can be just points where the curve changes direction. Of course, they can be points where the curve doesn't exist at all and has an asymptote too. But they can be points where the curve just changes direction. And if a curve is changing direction, it's either changing direction by a concave up or a concave down. So let me use red here. So for example, notice that this line has slopes. If I were to draw, these are supposed to be straight lines. If I were to draw slopes there, notice that those slopes are definitely increasing. So if slope's the first derivative, right? The first derivative is constantly changing as you go. This one here, it's steeper at the beginning, so the slopes would be higher, and then the slopes get lower. Remember, slope is always rise over run. Feel free to actually put, think rise over run. That's a small rise compared to run. This is a much bigger rise compared to run. This is a very big rise compared to a small run. And then same thing here, right? Big rise, small run, less of a difference between this rise and that run, and then this one would have very little rise compared to that run. So that's what happens when we call, these are two functions that are increasing, and in general, a function is said to be concave up on an interval if the graph of the function is above the tangent line at each point. If the function's below the tangent line at each point, then we call that concave down. So in the case of the two functions above, their concavity relates to the rate of increase. Now, this is also true for decreasing functions. You can read the notes in your own. We'll just kind of get to the main points here. Notice that this one, again, my slopes would start out as being negative but steeper, and then flatter as I go. That one's terrible. That's not even close to being a tangent point. Neither is that. Come on. Yeah, you get the idea. Trying to draw. I just can't make this one happen. There, that's as best as I'm going to do. Right? The slopes are definitely getting smaller as I go. And here, they start out small. That one would be almost linear, or almost horizontal, I should say. And then they're getting steeper as you go. Okay? So this is, again, concave up and concave down. Same thing. I guess I didn't write that in the first one. That's concave up, and that's concave down. And again, these notes, if you want all of the writing and stuff, they are shared in your OneNote folder. Okay, we consider again how the concavity relates to both the rate of the decrease and the sign of the second derivative. So one at a time here. This guy has, okay, remember, you can figure out if it's an increasing function without even doing with just doing a first derivative, right? So an increasing function, that was the first thing we did in chapter 5. And it's increasing because its first derivative is positive. It's concave up because, again, it's an increasing function. And its second derivative would be positive. In other words, you could say the rate of change is positive. A good analogy for this is for you physics folks. This would be the kind of situation where, well, okay, this has an acceleration, but the acceleration's increasing, right? So the speed is increasing, but it's increasing at a positive rate. Whereas the one on this side, this guy over here, that one's not quite the same, right? It's still going to have an increasing speed. As time goes on, it's increasing in its speed, but the rate that it's gaining speed is going down. So it's decelerating, right? Get it? It's still getting faster, but the rate at which it's getting faster is slowing down, if that makes sense. Okay? And of course, these ones would be basically on the bottom here the same, but in the opposite direction, right? So remember, acceleration and velocity are vectors, right? They have a magnitude and a direction, which means they can be positive in one direction, negative in the other direction. So, but it's the same exact idea, right? It's concave up, right? But, and f prime primed is positive. Here it's concave down, and f prime primed is going to be negative. So that leads us to a test for concavity. If f is concave up, that means that f primed is increasing and f prime primed is positive. If a function is concave down, its first derivative is decreasing and its second derivative is negative. So let's look at a diagram of something like that. This you might want to make a quick sketch of. Example 1. Determine the intervals on which the function with the graph on the right is defined is concave up or down. So it looks like it's defined all the way from A to whatever this point is. They didn't give us a point for that. I guess we could call it C if you like. Or actually, no, I guess not. You know what? I think my diagram got cut off. Don't put a C there. You know what you're supposed to put here? I think there's supposed to be an arrow on here, and I think it got cut off. Put an arrow on that. Yeah. Yeah, there's supposed to be an arrow on that. Sorry, it got cut off. Okay, anyway, there we go. We would say that this thing is concave up from B to infinity, right? And we would say that it is concave down from A to B. Okay, so there's my two intervals. And the point at which it's changing from concave up to concave down is called the inflection point. That would be a critical point if I did the first derivative test. But notice it would have failed that interval test that would have told me that it's a local maximum or a local minimum, because it's going down this way and it's going down that way, right? So it would have been the same direction in both cases. So I'd have known, oh, that's not a local maximum or a local minimum. Well, what the heck kind of point is it then? Well, the second derivative test is going to tell me that it's where it changes from concave down to concave up. So it's a point where the direction changes. Or maybe to put it better, right, it's the point where concavity changes. So B comma f of B is going to be my inflection point. Okay, and the rule for an inflection point is a function has an inflection point at some C if f primed of C is 0. In other words, that's why we call this, that's why my pen just stopped working. Come on. Oh, it's so early in the day for this to be a problem. There we go. Oh, still no. Come on. There we go. That's why we call this the second derivative test. Okay? And note that if f prime primed of C is either 0 or undefined, we still call that a critical point, right? We still say critical value, but it's the critical value of the second derivative, not the first. Okay, let's get to some actual calculations here. Oh, actually, we still have some diagrams, sorry. There's three different possible ways. If you have an inflection point, there's three cases that could happen. Okay, if the inflection point is point C, and on the left of C, you're negative, and on the right of C, you're positive, you're going from concave down to concave up. In other words, something like this, where that's C. If C is a point of inflection, and you go from positive on the left to negative on the right, that means you go from concave up to concave down. So that'd be something more like this. That'd be something more like this. That'd be, oops, oh, sheesh. Let me draw that better. So that'd be something more like this, right? It was concave up, and then it became concave down. And then, of course, case 3, just like the first derivative test, where we, oh, hey, look, we've got a point, a critical point where the slope is 0, or it doesn't exist. Does that mean that has to be a local maximum minimum? No, it might not be. Same thing here. There is a case where it's possible that it isn't an inflection point. It just turned out that that was a critical value. And that what would happen there is that the direction in which it's concave wouldn't change when I do the interval test. So if it's concave up and then I check on the left, it's on the right, it's still concave up, then that's not an inflection point. If I check on the left, it's concave down, and on the right, it's still concave down, then it's not an inflection point. So the inflection point test is basically this. Find your second derivative, set it to 0, and find all the critical points. Use the number line to classify the critical points into 3 cases, into one of the 3 cases we just looked at. If f prime primed of x changes sign at c, in other words, it goes from being positive to negative or negative to positive, that's an inflection point, and that means the concavity changed. If f prime primed of x doesn't change, then it is not an inflection point. Let's do a couple of calculations now. All right, so jot down example 2. We got a cubic here. All right, so f primed of x is, of course, going to be 3x squared plus 6x minus 9, which means that f prime primed of x is going to be 6x plus 6. So let's do the test. Let's set the second derivative to 0, in which case we're going to factor out a 6 here, and x equals -1 is my critical value of my second derivative. So let's do a little test on that. So we're going to, I'll just use a number line since it's linear. I don't need a big interval chart for something linear. So, oh, that's not supposed to be 0, that's supposed to be -1. So at -1, what happens? Okay, let's pick a number smaller. Let's find, say, f prime primed of -10. That's definitely smaller than -1. Okay, so f prime primed of -10 is going to be -60 plus 6. Well, that's definitely going to be less than 0. So if it's less than 0, that means that we have a negative here, which means that we have this kind. We are concave down. All right, let's pick a number bigger than -1. How about 0? What's f prime primed of 0? Well, that's definitely going to be 6, so that's going to be greater than 0. So that's positive, so that's going to be concave up. Okay. So I know that I am concave down. A little better. Concave down from -infinity to -1. And I know that I'm concave up from -1 to infinity. So there's my intervals of change of direction. And I would say, therefore, that x equals -1 is an inflection point. And if it's a point, of course, I kind of want to know the y-intercept too. Now, don't forget that you have to go back to the original function. So I actually have to figure out what f of -1 is, not f primed of -1 or f prime prime. Go back to the original function, and let's see. -1 plus 3 is 2. 2 plus 9 is, what is it? Hang on, do I have that right? 2 plus 9 is 11. Hang on, do I have that right? Oh, -1. I better do this the right way here. -1 plus 3 plus 9 minus 8. Is that right? So that's going to be 3. So it's 2, 11 minus 8 is 3. Yep, I think that's 3. So that is equal to 3. And there goes my pen again. So that's going to be -1, 3. And let's just see if I'm right about that. Does this thing change direction? I have this graphed on Desmos. And here we go. Looks pretty good, right? It's concave from here, right? That's concave down. It's a frown. And then right around here, it changes direction and starts going concave up. So where is that point again? Right there, at -1,3. It changes from being a downward to an upward, from a frown to a smile at -1,3. Okay, so there's the first example. Let's go to another one. Okay. All right, now this one's kind of messing with us. What do we know about this one? Think about our last lesson. What kind of thing does this one have that the last one didn't? Yep. This one has a vertical asymptote at x equals 0. Okay, I'm going to save the work here because I want to get through one more example after this, and I don't want to run out of time. I'm just going to say, all right, I already used quotient law on a piece of scrap paper over here, and I found that after my first derivative is x squared minus 4 over 2x, and my second derivative, again, I did this on scrap paper, is 4 over x cubed. Feel free to run that through for yourself when you get a chance if you want to prove that that's true and do a little practice. So that would tell me that I have, move this up, a critical value. Remember, critical values are places where the derivative is 0 or doesn't exist. And notice it still doesn't exist when x is 0. So it's a critical value at x equals 0. But I still kind of know, oh yeah, but it's a critical value, but I know it can't be an inflection point. How come? Because it's got an asymptote there. But you know what? It's still nice to know, okay, so what's happening on either side of the asymptote? Is it concave up or concave down? Is it a bit of a smile or a bit of a frown? And the test still tells me that. So I'm still going to use a number line here. And I'm going to put 0 this time. And let's see, f prime prime, pick a number smaller than 0. So let's pick -1. And 4 divided by -1, that's definitely a negative. And I don't know why I used an equal sign. I wanted to use a less than sign. It's negative. So that's a negative, so that's a frown. Or concave down. And then let's do f prime primed of -1, of something bigger. I meant to say +1 there. Of +1. And you'll see that that's positive. So that's positive, so we're concave up. So look at all that we know here. We know, maybe I should put this in words. We know that x equals 0 is not an inflection point. Because it is a vertical asymptote. Right? The function's not actually defined there. But I still know that I'm concave down from -infinity to 0, and I'm concave up from 0 to infinity. So I can kind of picture this in my head, right? I know how functions behave as they approach asymptotes. They get closer to them. Ooh, I actually could also do a quick horizontal asymptote on this one, right? Very often when you have those two arms, one going to -infinity, one going to +infinity, they also have a horizontal asymptote of 0. In other words, the x-axis becomes a horizontal asymptote, or some other horizontal lines in asymptote. Is that true here? Could you do kind of in your head a quick limit test? I don't want to spend a whole lot of time on it. But if you did a limit test on that, divide top and bottom by x squared, what do you get? You actually get infinity, right? So the limit as the limit as x approaches my asymptote of 0 of f of x is actually going to infinity. So it actually doesn't have a horizontal asymptote. And let's see if that's true. Let's go to, oops, that's what I wanted to do. Let's go to my Chromebook here and and yep, check it out. right? This is definitely a concave up. You're probably thinking, well, it's not really concave, but yeah, it is. This is actually going up, right? And hey, my horizontal asymptote test told me that. It is not a horizontal asymptote. It is getting up. I mean, it's slow, but it is going up forever. And then this one is, of course, going to go down forever. I didn't bother doing the asymptote as I headed towards 0 from the left side, but I actually know that it's going to do the same thing. So there we go. Cool. All right. Let's go back to my notebook. There we go. So that was example 2. And then kind of just a quick summary here. The second derivative test tells us about concavity, but oh yeah, another thing it can do is it can help us determine where I have maximum and minimum values. Because think about it, if something is concave down, or sorry, I should say concave up. If something is concave up, it's a smile, must have a minimum somewhere, right? If something is concave down, it's a frown, it must have a maximum somewhere. So the second derivative test can actually help us find local maximums and local minimums too. You can say that if you have the first derivative is equal to 0, but the second derivative is positive at 0, or at the point C that gave you the 0, then you know you have a local minimum. If the first derivative, when you set it to 0, or if the first derivative is 0 at some point C, and then the second derivative at that point C is negative, then you have a local maximum. Let's try that. So find the local maximum and minimum values of x cubed minus 12x plus 5. Okay, so first derivative. First derivative is 3x squared minus 12x. Or no, sorry, just minus 12, right? There we go. So that means the second derivative, well, first let's set that to 0, right? So let's find out what x is when that's 0. So that's going to be 0 is equal to 3x squared minus 12. Divide both sides of the equation by 3. And I have 0 is equal to x plus 2, x minus 2. So I have critical values of the first derivative at x is 2 and negative 2. Okay, now we need the second derivative. So f prime primed of x is going to be 6x, right? The minus 12 becomes 0. So let's find out the two things. What is f prime primed of, let's start with the 2. Well, if you put a 2 in for 6x, you get positive, right? Okay, so that means, look at the rule. If the second derivative at the point that made the first derivative 0 is positive, that's a local minimum, and I'd go back and figure it out what f of 2 is. Turns out that f of 2 is negative 11, so my local minimum is at 2, negative 11. And, oh, and of course, I know then also that I'm, if it's a local minimum, that means I'm concave up, like that, right? And let's do the other point now. What happens to f prime primed of negative 2? Well, f prime primed of negative 2, put negative 2 and you get a negative. 6 times negative 2 is negative 12, so that's a negative. Therefore, x equals negative 2 is a local max. So I have that happening. And of course, I'm going to want to know what f of negative 2 is. I already worked this out. It turns out to be 21. So at negative 2, 21, I have a local maximum, and at 2, negative 11, I have a local minimum. Let's just see if I have that right. Let's go to Desmos. Desmos. There's the function. Yep, looks to me like I have a point here, right? Point there. Let's see, are they the right points? Yep. Negative 2 and 21, negative 2, or positive 2 and negative 11. Local max, local min. And I could have found my inflection point. Looks like my inflection point's somewhere between these two things. Okay, how would I have found the inflection point? Let's go back and do that. Let's go back and do the inflection point. So what's the inflection point test again? It's where the second derivative is 0, right? So let's go back and do that. Maybe I should have done that before we went to this diagram, sorry. So let's see. Let me just get some room here. F prime primed of x is 6x. Set that to 0, and you get 6x is 0, so x equals 0. Now, unlike the last time where we had an inflection point maybe when x was 0, it turns out we couldn't even have 0 in the last example because it was an asymptote. It didn't exist there. Well, this function is cubic. It definitely exists when x is 0. So what is f of 0? F of 0 is 5. So therefore, 0, 5 is an inflection point. Now, how did I know that that's an inflection point? Well, oh yeah, because I've already kind of figured out that before and after that 0, I go from being concave in one direction to concave in the other. Concave up, concave down. So I know that that must be an inflection point. And let's go back and take a quick look and make sure that I'm right about that. Is that where that is? Oops, that's the same thing. Don't do that. There we go. 0, yep, 0, 5. So there we go. That takes us to the end of all of the new stuff we're going to do for curve sketching. And we'll assign a few questions for you to try in 5.4. We won't even assign anything in 5.3. 5.4 is kind of the more important one. And then tomorrow we'll just kind of put it all together and look at all these things at once. And that's it for curve sketching. Okay, turn off the video now. Look at that, I finished with like a couple minutes to spare even, but I went really fast. Sorry about that.